We will now consider the chi-square statistic, which is used with cross-tabulation. So let's go into our descriptive crosstabs. Let's do mom in the rows and the child in the columns. And let's go to our cells and let's choose expected. We'll talk about why we're doing that in a minute. Let's do our chi-square statistic. Now, what do we have here? So, the null hypothesis for chi-square statistic is that the cells, given the marginal totals, these cells do not vary from chance. Now, what is chance? What is chance for a mom not being myopic and the child? So if there was no relationship, because we're looking at the relationship between these two variables, and it's not like in a correlation where there's order in the number, although actually there is order when there's only two levels, but when there's more than two levels, there were three, like in the parental myopic, there's 0, 1, or 2 parents. I guess that's order too, but there's we just look for an association between we're testing for an association between these two variables. And so the probability of by chance is what the expected count is. And so given this marginal total, there's a probability that a mom is not myopic. There's a probability that she is. There's a probability that the child was not myopic. There's a probability that the child was. If you multiply this probability times this probability, you get the chance probability that this is true. And multiplying that probability times the total 3298 gives you the expected value. So it's expected by chance that this cell contains 2094 observations. And it's a little bit more than that in actuality. So let's look at the formula for chi-square. Chi-square is looks like this. And that equals an observed value minus its expected value. And this is something like in a standard deviation, we have an observation, an x minus the mean of x. It's the same exact concept. And we square it. And then we're going to divide by the expected value. Now the reason we divide by the expected value is that it turns out these counts are Poisson distributed, and Poisson has the convenient characteristic that the mean and variance are equal to the same thing. So this is essentially, not only is it the mean, it's also the variance. So think about your standard deviation formula. It's observed minus, or a t-test rather, observed minus a mean over a measure of over the standard deviation. We don't take the square root of this like we do in the other program, so it's a chi-squared. Now, this is the observed value in a particular cell, like the number of moms with myopia, and the expected number of value for the number of moms with myopia over the variance. And this is for each cell, the variance in that cell. So this is for each cell, and then you add it up over all the cells, and that's the chi-square. So here we have, and it was invented by Pearson. He did a correlation coefficient. He also did this chi-square formula. And in this particular case, we get a value of 6. And the two-tailed significance for that is 0.014. So that means that there is an association between moms with myopia and kids with myopia. Now, if we look at this formula, we see that the number of children that were never myopic with the moms never myopic is actually a greater number. So there, instead of being the chance given these marginal totals, there's actually a few more nevers. Similarly, down here, 154 is higher than 131. So if it was chance, you'd get 131, but there's actually more kids that developed myopia during the study if their mom was myopic. It's not a big difference, but it is significant in this case. And significant is that there's a null hypothesis. Also, the sample size is pretty large, so that's an issue too. But in fact, we found that there was an association, or at least we rejected the null hypothesis, saying that we rejected the notion that there was no association. So our p-value at 0.014 is the probability of getting this value if the null hypothesis was true. So that's the chi-square. Some assumptions that must be met in order to do this test is that the values, the expected values in these cells have to be at least 5. And in this case, there's plenty more than that, but they need to be 5. It's not the frequency that needs to be 5. It's the expected value that needs to be 5. Very important distinction. It's perfectly okay to have 0 cases as long as the expected value is 5. Continuity correction is done when you fail to meet that assumption. Also, Fisher's exact test is used for that. For small samples where you don't meet your expectations. Actually, a lot of times the continuity correction is used when you have a 2x2 table rather than reporting the full chi-squared. And that's simply looking at our formula and taking the absolute value here, and we would get rid of that little guy, subtracting it from 0.5, and squaring this whole thing. That's the continuity correction. It's done because we just have 2 categories and we're trying to estimate basically the Poisson distribution, which is basically estimating the normal distribution with a large number of observations. So that is our chi-square test. The Fisher's exact test is based on probabilities. We won't go into that.